In this section, we will explore the concept of atomicity. What is atomicity? The term atomicity comes from the Greek word atomos, meaning indivisible, emphasizing that a transaction is treated as a single, unbreakable unit. Originates from the ACID model of database systems introduced in the 1980s. Atomicity is one of the ACID properties: atomicity, consistency, isolation, durability. Ensures a transaction is all or nothing, either all operations succeed, or none are applied. Prevents databases from becoming inconsistent due to partial updates. First, the start block appears. This marks the beginning of the operation. The system plans to update the variable x, but no action has been performed yet. The value of x in main memory is still 10. Read x equals 10 block. Here, the processor reads the value of x from main memory and loads it into the CPU for processing. It only copies the value and does not modify the value stored in memory. Then, updation in CPU block appears. The CPU performs the addition and calculates the new value as 15. However, this updated value exists only inside the CPU. The main memory still contains the old value x equals 10. Then, the failure occurs. It represents an unexpected event such as a power failure or interruption. The failure happens before the updated value can be written back to memory. Finally, the write block appears, but the write does not happen. Because of the failure, the value 15 is never stored. The memory continues to hold x equals 10, showing that the operation was only partially executed. Non-atomic/partial execution. This slide explains a non-atomic operation, where an update is performed in multiple separate steps and can be interrupted before completion. Start. This step represents the beginning of a non-atomic operation. The system intends to update the shared variable x. At this moment, the value of x stored in main memory is 10, and the operation has not yet started execution. Read x equals 10. In this step, the processor reads the value of x from main memory and loads it into a CPU register or cache. The value read is 10. This read operation only copies the data for processing and does not change the value stored in memory. Add 5x equals 15 in CPU. Here, the CPU performs the arithmetic operation by adding 5 to the value it has read. The result becomes 15. However, this updated value exists only inside the CPU register or cache. The main memory still contains the old value x equals 10. Failure occurs. At this point, a failure such as a power loss, system crash, thread interruption, or context switch occurs. The failure happens before the updated value can be written back to memory. Because the operation is non-atomic, the system allows such interruptions between individual steps. Write x to memory, not done. Since the failure occurs before this step, the final write operation is never executed. As a result, the updated value x equals 15 is lost, and the main memory continues to store the old value x equals 10. Final outcome. The operation is only partially executed. The read and computation steps are completed, but the write step is missing. This leads to an inconsistent or incorrect system state because the intended update does not fully take effect. This slide explains an atomic operation, which follows the all-or-nothing execution principle. Atomicity means that an operation is executed as a single, indivisible unit. Either the entire operation completes successfully, or none of it takes effect. Next, the before, x equals 10. This shows the initial state of the system. The value of the variable x stored in main memory is 10. At this point, the data is consistent and no operation has been applied. Then, the atomic plus 5. This represents an atomic operation that adds 5 to the value of x. Although internally this may involve reading the value, performing the addition, and writing the result back, all these steps are treated as one single unit and cannot be interrupted or observed individually. After that, the execution splits into two possible outcomes. On the left branch, the after, x equals 15. This represents successful execution of the atomic operation. The addition is fully completed, and the updated value is written back to memory. The system moves directly from x equals 10 to x equals 15 without exposing any intermediate state. On the right branch, the after, x equals 10. This represents a failure scenario such as a system crash or power loss during execution. Because the operation is atomic, the system automatically aborts the operation and discards any partial changes. The original value of x remains unchanged at 10. The key takeaway from this slide is that an atomic operation guarantees data consistency. There is no partial update. The final value of x is either fully updated to 15 or remains at the original value 10. Atomic/all-or-nothing execution. This slide explains an atomic operation, where an update is executed completely or not executed at all. Partial execution is not allowed. Before, x equals 10. This represents the initial state of the system. The variable x is stored in main memory with a value of 10. At this stage, no operation has been applied, and the data is in a consistent and stable state. Atomic +5. This block represents an atomic operation that performs the update x equals x plus 5 as a single, indivisible unit. Although internally the system may read the value, perform the addition, and write the result back to memory, these steps occur as one unit and cannot be interrupted or observed individually by other processes. Indivisible nature of atomic operation. During the execution of this atomic block, no other process or thread can observe any intermediate value or interfere with the operation. The system guarantees that the operation will either complete fully or not be executed at all. Successful completion after x equals 15. If the atomic operation completes successfully without any failure, the updated value is written back to main memory. The final value of x becomes 15. The system moves directly from one consistent state to another consistent state without exposing any partial result. Failure during execution after x equals 10. If a failure such as a power loss, system crash, or interruption occurs while the atomic operation is in progress, the system automatically aborts the operation. Any partial changes are discarded, and the original value of x remains unchanged at 10. Rollback mechanism. The rollback mechanism ensures that the system does not enter an inconsistent state. Even though the operation may have started, all its effects are completely undone, preserving data correctness and system stability. Final outcome. There are only two possible outcomes in an atomic operation. Either the update is fully applied and the value of x becomes 15, or the update has no effect and x remains 10. No intermediate or partial state is ever visible to the system. Why atomicity is required? Atomicity is essential in parallel and distributed systems to ensure reliable and consistent operations. Prevents race conditions, ensures multiple threads or processes don't interfere when accessing shared data. Guarantees correct outputs, multi-threaded programs produce consistent, expected results. Ensures data integrity, critical in distributed databases where operations span multiple nodes. Avoids partial updates, protects against failures like crashes, network errors, or power outages. Example. If two users try to update the same file simultaneously. Without atomicity, partial writes can occur, causing file corruption. With atomicity, the update happens all or nothing, keeping data consistent. Atomicity in parallel computing, shared memory. Multiple threads accessing shared data. Parallel programs often use shared variables, counters, buffers, and similar resources. Even a simple operation like x equals x plus 1 involves multiple steps. If multiple threads interlead these steps, it can lead to incorrect results. Example, lost update problem. Shared variable x equals 7. Thread A. Step 1, reads x_a equals x equals 7. Step 2, computes x_a plus 1 is equal to 8. Meanwhile, thread B might also read x equals 7 and write back 8, overwriting thread A's update. This illustrates why atomic operations are critical in shared memory parallel computing to prevent race conditions and data inconsistency. Lost update problem, continued. Thread B, concurrently. Imagine thread B is trying to update the same shared data at the same time as thread A. Both threads read the current value, then calculate their update. Because they are running concurrently, their actions can interleave. Thread A might write its update just before thread B writes its own. As a result, thread B overwrites thread A's update, and the shared data ends up incorrect. This is called a lost update. The expected final value should reflect both threads' changes, but because of interleaving, only one change is applied. The atomic fix ensures that each thread's update happens as a single, indivisible operation. Now, thread A completes its entire update before thread B starts, so both updates are applied correctly, and the shared data stays consistent. Outcome. Using the atomicity property, the final value of X becomes. Applications of atomicity. Banking transactions, guarantees that transfers, deposits, and withdrawals happen all or nothing. E-commerce order processing, prevents partial order fulfillment or incorrect inventory updates. Stock trading systems, ensures buy and sell operations are consistent and accurate. Shared counters in multi-threaded programs, prevents lost updates when multiple threads increment counters simultaneously. Concurrent queues and buffers, ensures NQ and DQ operations in producer-consumer models are safe. Distributed databases and replication, maintains consistency across multiple nodes during updates. Advantages and disadvantages of atomicity. Advantages. Ensures consistency, prevents partial updates, keeping databases or shared data in a valid state. Prevents race conditions, multiple threads or processes can safely access shared resources. Reliable transaction management, all operations in a transaction succeed together or fail together. Fault tolerance, protects against crashes, network failures, or power loss by rolling back incomplete operations. Disadvantages. Performance overhead, using locks, mutexes, or atomic instructions can slow execution. Complexity in implementation, requires careful design in multi-threaded or distributed systems. Potential for deadlocks or starvation, improper synchronization can block other threads. Limited granularity, fine-grained atomicity can be expensive, coarse-grained atomicity may reduce concurrency.